Your model just approved a loan or flagged a transaction, and someone asks the obvious question. Why? Most important scores you'll get back are ad hoc. One tool ranks features one way, another tool disagrees, and none of them can promise the numbers even add up. Shap fixes that by borrowing an idea from game theory that's almost 100 years old. It hands each feature a fair share of the credit with actual math behind the word fair. Here's how it works. Before we get into the mechanics, look closely at the problem Shap is really solving, because that's where its whole appeal comes from. Most feature importance is ad hoc. You get a number that says a feature matters, but different methods hand you different rankings, and there's no guarantee the scores relate to the actual prediction in any principled way. Swap the method and the story changes, which is a bad place to be when you're explaining a decision that affects a real person. Shap takes a completely different route. It reaches back to the Shapley value from cooperative game theory, and that gives it a set of fairness axioms nobody else can claim. The contributions provably add up to the prediction, symmetric features get equal credit, and a feature that changes nothing gets exactly 0. Fair here is a theorem, not a vibe. So how does an idea from economics end up explaining a neural network? Walk the logic once and it clicks into place. Picture the features as players in a game and the prediction as the payout they're splitting. Each feature is a teammate that either shows up or sits out, and the model's output is the prize the whole team earned together. Now, the fair share of any player is its marginal contribution, how much the payout grows when that feature joins the team. The catch is that the contribution depends on who joined before it, so you can't just measure it once. That's the clever part. You average a feature's marginal contribution across every possible ordering of adding features in. Every sequence, every arrangement, all of it averaged together. That average is the Shapley value, and it's the one attribution that keeps all the fairness axioms at once. And here's the payoff. When you add up every feature's Shapley value, the total lands exactly on the prediction minus the baseline. Nothing leaks, nothing is double counted. The explanation reconciles perfectly with what the model actually output. Strip it down and 3 ideas carry the whole method. Shapley values at the core. The credit each feature gets comes straight from cooperative game theory, treating the prediction as a payout to be divided fairly among the features that produced it. Fairness you can prove. Shap is the unique attribution satisfying its axioms at once. Efficiency so the parts sum to the whole, symmetry so equal features get equal credit, and 0 for anything irrelevant. Fast enough to actually use. Exact Shapley values are exponentially expensive to compute, so Shap ships clever approximations like tree Shap, which is exact and quick on tree ensembles, and kernel Shap, which works on any model at all, which is why Shap unified several earlier methods under one roof. Alright, let's lock in the essentials. Shap explains any model's prediction by assigning each feature a Shapley value borrowed from cooperative game theory, from a paper by Lundberg and Lee in 2017. That value is a feature's average marginal contribution across every ordering, which makes it the unique attribution that satisfies the fairness axioms. Because the contributions sum exactly to the prediction, Shap works for a single local explanation and for global importance when you aggregate many of them, with tree Shap and kernel Shap making it practical. Understand Shap and model explanations stop being guesswork. If you like your machine learning demystified this cleanly, Standarity.com has a whole shelf of these explainers waiting. See you there.